Welcome! In this video I'll show you how to solve any integral that is of this kind. That is r to some power, which can be any power, times e to the minus some constant b, times r, again r the constant of integration, dr. So this integral pops up all the time in everything quantum. So quantum mechanics is where you're going to encounter it literally all the time. And you're going to find different versions of it. So sometimes it's going to be r to the power of 2, to the power of 3, to the power of 4. You can literally find it to any power. And it's very, very useful to know the formula so that you don't have to go through the trouble of solving it, because it can be a little bit annoying. It's not really difficult, but it will take you some time. And it's just a nice thing that you can learn to avoid. So the way that we want to solve this is, first of all, notice what is up here on the exponent. So it's very important that there has to always be a minus sign in the exponential. If there is no minus sign, then you're going to have an integral of a different kind, and the formula that we'll find will not be useful to you. And also you have to bear in mind the limits of integration. If you're not integrating from 0 to infinity, you can use some of the same procedures, but the end result will of course not be the same. All right, so with that in mind, once you begin here, you could in principle just integrate by parts right away. I like to simplify things just a little bit by doing a substitution. So the best substitution to use here is, say u is equal to br. Now it has to be br. Adding the minus sign in here will not make things particularly easy for you. So I do recommend that you take u equals to br. And of course, then if you're substituting, you find du, which is simply going to be b dr. All right. And from here, of course, you can find r, which will be just u over b, and dr, which will be du over b. Okay, so with this in mind, you can just plug this into the integral. Now the limits of integration don't change, because when when r is 0, u is 0, and when r is infinity, u is infinity, so they don't change. So instead of having r, you end up having u over b to the power of n, and you have e to the minus u, and instead of dr, you have du over b. Okay, so just from doing this change in variable, what we're going to have is going to be 1 over b to the n plus 1. Okay, so that is b to the n from here times b over here. And of course, now just the rest of the integral. So integral from 0 to infinity of u to the n, e to the minus u du. So I do want to emphasize just once more that this is basically the same integral that we had before, but just with, at least here, just with b equal to 1, even though of course we took the b outside. But I just want to emphasize that you can find different versions of this integral when we are doing, you're studying physics or doing mathematics or something. So just keep in mind, b is going to be changing. Sometimes it's not even going to be just a number, right? In the case of the hydrogen atom, you can find r over Na, for example, and here your b would be 1 over Na. So that is just one example where you can find it. Okay, now we want to solve that integral, and to do that, we are going to integrate by parts. So we are going to integrate here, and this is going to be, well, let's call I this thing right here. So this is going to be I, and let's define our variables here. So I already used u, and I don't want to use it again. So let's say v, which is going to be, so looking at this, v is going to be, now the easiest thing is going to be to take u to the n. And in fact, that is what you have to take. Otherwise, you're not really going to get very far, because now every time that you take the derivative, you're going to get 1 power less. So you're going to get n times u to the n minus 1. And that is the key behind this procedure. That every time you integrate, every time you do integration by parts, we're going to end up, as you will see very shortly, with this same integral, but the exponent of the u will be a little bit smaller. So if you do this n times, it's going to be completely gone, and you will simply be left with the integral of an exponential, which we can easily solve. So the second part here, let's call it the w. This is e to the minus u du. So w is going to be minus e to the minus u. Now this pencil is a little bit too thick, so I will just do it there. Okay, so with this in mind, let's now write down I. So the integral, and keep in mind, I'm just solving this integral, so when we finish with all of this, we're going to have to plug this 1 over b to the n plus 1 in front, so do not forget about that. So the integral here is going to be first u to the n times this, so minus u to the n e to the minus u, evaluated between 0 and infinity, minus the product of these two integrated. So that means integral from 0 to infinity of n to the u n minus 1. And now there's another minus sign, so this becomes plus, and e to the minus u du. Now notice that this first part, what is it going to be? So evaluated at infinity, here we get e to the minus infinity, which is 0. And evaluated at 0, this thing will be 0. So we get 0 minus 0, right? Both ends are going to be 0, so we simply get 0. Now so that's 0. Now from this integral, we can factor out n and just see what we get, because now we have u n minus 1 e to the minus u du. And you can see now that it is exactly the same that we had up here, except that now instead of having u to the n, we have u to the n minus 1. Okay? And if we now do integration by parts again, since it's exactly the same integral, all we did was, in the end, right? Everything we did in the end was take this number n, put it in front of the integral, and then just reduce it, right? So if we take another integral by parts here, we get n times n minus 1. Here I'm, of course, jumping over a few steps. The steps are exactly the same that what we just did. That is why I'm jumping over them. So here we have integral from 0 to infinity, and we have u to the now n minus 2 e to the minus u du. And we can do this again and again and again and again, right? So we do this the amount of times until we get something like n times n minus 1 times n minus 2 times n minus 3, n minus 4, blah, 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 until eventually we get times 2 times 1, right? And we get to the point where we have the integral here of u to the n minus n, right? We did this n times, and then that's u to the 0, so that we don't need to write the u, and then we have e to the minus u du. So all we need to do now is write or solve this integral. Now the thing in front here, this is simply n factorial, right? That's the definition of n factorial, and this integral is easy to solve. It's simply the integral of the exponential. So that's going to be minus e to the minus u evaluated between 0 and infinity. And here, let's now simply just evaluate this. So we get at infinity, it's going to be 0. So we get minus minus, because we now have to evaluate at 0. So we have plus e to the minus 0. So simply e to the 0, which is 1. So we simply get n factorial. Okay, but that is this integral that I have in the blue box right here. So that means that the integral that we started out with is 1 over b to the n plus 1, and we now multiply this by n factorial. Okay, so this is now the result. So let me maybe write this very, very clearly here. So if we have the integral of let me just write this a bit more clear. So integral from 0 to infinity of some r to the n e to the minus br dr, this is going to be this thing right here. So let's just see some random examples. So let's say we're calculating some expectation value of the hydrogen atom or something. And there we often find integrals like this. So maybe we have to integrate from 0 to infinity, right? Because in that case, we integrate over all of space. And we have r to the 4th, right? And e to the minus, let's say, 2r over na dr. So we want to integrate this. So we could just do integration by parts 4 times, which would be annoying, or we can remember this, right? We can Keep in mind that we know the formula. So what is b? B in this case is 2 over NA, but we have 1 over b. So that means that this is going to be NA over 2 to the power of n plus 1. What is n for? So this is now to the power 5. And then we still have to multiply by n factorial. So this is times 5 factorial. And well, of course, now we can still just go ahead and simplify a few things. So 5 factorial is 5 times 4 times 3 times 2 times 1. So you could simplify those numbers with this a little bit. But this is just to show you how easily you can solve integrals like this. And as I said, they pop up very often. So if you're taking any course on quantum mechanics or even beyond, these sort of integrals appear very often, so often that it really is worth it that you learn how to calculate them. So there it is. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. I'll see you in another video. Thank you very much for watching.